Bom dia a todos. É uma satisfação estar curtindo, né, esse nosso congresso. É uma delícia, né? Eu acho que isso passa para todos, a gente aumentar o conhecimento, né? Recarregar as baterias do conhecimento, é muito bom. E a gente está conseguindo ouvir coisas geniais, né? A gente às vezes até já acha que já sabe alguma coisa e de repente vem outros colegas e amplia a visão que a gente tem de um determinado assunto. Eu estou muito contente. Espero que vocês também. Hoje, ontem teve um dia bem cheio. E alguns dos senhores e senhoras e senhoritas que não tiveram oportunidade, tem uma arena criativa aí que está bombando. Acabou todas as inscrições e teve todos, muito bacana, uma coisa nova. Primeira vez que a gente está implantando isso. Fiquei impressionado também com o concurso dos estudantes, lá quem sabe faz ao vivo. Tinha até um mascote do Mackenzie lá. Mascote, bandeira. Olha, incrível essa energia dos jovens, dos engenheiros de amanhã. Muitos de nós aqui começamos assim também, começamos nos concursos do IBRACON, há alguns anos atrás. Então, está muito interessante isso. Tem curso hoje acontecendo e essa palestra aqui. Hoje a gente tem outros seminários também, né? A gente tem um seminário de novas tecnologias, que é no Espaço do Conhecimento, o seminário de pisos industriais. Pisos industriais é algo bem técnico. É difícil fazer um concreto sem fissurar. Precisa ser bom, precisa conhecer, com resistência à abrasão, né? Ou com aderência, mas que seja durável. Então, pisos industriais é um seminário interessante que vai acontecer hoje. Vai acontecer também o de assuntos controversos, com o professor Bernardo Tutiquian. O professor Bernardo é um showman, né? Ele é legal porque ele cria uma polêmica bacana no encontro. Também a gente tem um seminário de pré-moldados. Não dá para imaginar, gente, que nós vamos conseguir aquelas metas de 2050, 2060, sem passar pelo pré-moldado, sem passar pela industrialização, racionalização, industrialização. É a maneira que a gente tem de potencializar os nossos conhecimentos, nossos recursos. Então, vai ser muito legal. Recomendo vocês assistirem. E a Ilha estava me lembrando que a gente também tem, agora às 10 horas, quando terminar aqui, o lançamento da prática recomendada do Comitê Técnico, é 304, né, Ilha? 304, de pré-moldados. Tá? Isso no estande do IBRACON, vai ter o lançamento do livro. Lembrando que todos os livros que estão sendo lançados com 50% do valor depois de... Aí o cara fala assim, poxa, mas devia doar os livros. É que é uma fonte nobre do Instituto. O Instituto precisa sobreviver, sabe, gente? Pagar os funcionários, pagar o aluguel da sede. E essas coisas, com esses recursos, é que a gente mantém o Instituto. Nenhum dos diretores, nossos cargos são todos honoríficos, a gente não tem benefício nenhum. Os nossos direitos e deveres é igual a de qualquer sócio. Mas a gente paga a inscrição aqui. Todos os diretores pagam a inscrição no evento. É bom que vocês saibam isso. A gente não tem privilégio nenhum. Mas o Instituto precisa sobreviver, e uma renda nobre do Instituto é essa, é publicação técnica, científica, é a inscrição aqui no evento para que a gente possa pagar, né, custear todas esses benefícios que a gente tem aqui, comodidades, essa infraestrutura. E a gente também tem o seminário de durabilidade, também muito com gente do exterior, né? Vocês viram que a quantidade de colegas de entidades e de profissionais que a gente usa na bibliografia, que a gente aprendeu com eles, é muito grande. Então, convido vocês todos assim se envolverem com o nosso congresso. Bom, hoje a gente tem uma apresentação agora, de que a gente chama de plenária, que a gente chama de plenária, que é muito especial porque o professor Ravinda, que eu já vou chamar daqui um pouco, ele é um grande amigo. Eu conheci há uns 25 anos, alguns de vocês não eram nem nascidos, né? Dos mais jovens, lá em Barcelona. E ele tinha feito doutorado nos Estados Unidos, em centros de pesquisa muito reconhecidos, e nós nos conhecemos lá. E tive a felicidade de, inclusive, participar da banca do primeiro doutorado que ele orientou, e que era de uma brasileira, a professora Berenice, do Paraná. Então, é uma satisfação muito grande ter, porque ele sempre foi uma referência para nós. É um especialista em ensaios, em laboratórios, conhece muito essa parte, mas também tem a visão holística que é necessária para a gente fazer bem qualquer pesquisa. A gente empurra a fronteira do conhecimento numa coisinha pequena, mas precisa ter uma visão do conjunto para que tudo dê certo. Hoje ele deixou Barcelona, voltou para a Índia. Ele é professor titular, investigador titular em Madras, que é um instituto da Índia, o primeiro lugar, digamos, o mais importante, é um MPT da Índia, tá? Ele é o investigador lá principal da Índia. Então, vamos ouvir com muita atenção aí. Quero convidar, por favor, meu amigo, professor Ravindra Jetur.
Muito obrigado, Paulo. Es un placer estar aquí. Well, I'll switch to English so that the interpreter has it easier. It's a pleasure to be here on behalf of RILEM. So I happen to be the immediate past president of RILEM. On behalf of the current president, Nicolas Roussel, congratulations, parabéns. It's always a pleasure to come to Brazil, especially to IBRACON. This is my third talk in an IBRACON conference. First one was in Fortaleza, maybe about 20 years before. Selmo Cooperman was the one who invited me. I don't remember when it was, but the late 90s. And he was president then, and I believe he was one of the founders of IBRACON. So I have very special memories of Brazil. Have a lot of friends here. A lot of my students are here. And what I like a lot about this conference is the motivation, the new results that are presented, and the participation of young people. Well, also at my age, everybody is young, so that is different. But it is so nice to see so many young people. And when I travel, I always use the IBRACON conference as a reference, that every country should have a national conference focusing on young people, their talent, and their progression in their career. And IBRACON has done an amazing job. So it is certainly a pleasure to be here, especially invited by Paulo Helene, who I think is a reference on durability. He started talking about durability when the world did not care about durability. The world thought that concrete did not need any maintenance. It was said that only steel needed maintenance and concrete did not need any maintenance at all. We thought that if we design for strength, stiffness, deflections, the structure will last forever. And I remember Paulo from the beginning, from the time I know him, emphasizing durability. And yesterday, you heard from Dr. Kasuga-san that durability is very important in sustainability. So what I will talk about is how we have to look at things holistically. We should not just look at carbon footprint or just the waste, but everything. And for me, durability is the most important aspect of sustainability. And I will attempt to put everything together so that you have a vision of what we are doing. So the work that I will be presenting is basically that of two of my students in another group. So I'm from the group of technologies for low carbon lean construction. So we want to look at construction, reducing the carbon footprint, the embodied energy, and wastage. Wastage of time, wastage of production, and so on. So that is what we call lean construction. So I'll start with these objectives for sustainable development of the United Nations, which is very nicely set up with the top row related to people, what people need, what a person needs, hunger, education, and so on. This affects every person. The second row talks about groups of people. What is important when groups of people get together? The infrastructure, industry, reduction of inequalities. And the last row talks about the whole planet. All of us, independent of where we are affected by what is there in the last row. So what I want to say is sustainability is all of these, not just carbon. Carbon, of course, is very important. Carbon footprint is important, and greenhouse gases are very important, but we have to keep everything in mind. Just as we know now that construction is just not the structure. At one time, design was thought to be the most important part of construction. Design was the challenge. The designer was king. But now, we have to make concrete that lasts for 100 years, that is durable, that has low carbon footprint, and also give the strength and stability. So we are talking about many things that we'll have to look at so that it is relevant for construction. So some of these SDGs are listed here where construction has an influence directly on these different goals that the United Nations has set for sustainability. So at IIT Madras, we've been focusing on blended cements. We are looking at fly ash, slag, and a new type of cement that we call limestone calcined clay cement, or the admixture is limestone calcined clay, and I'll talk about it a little bit more. And the idea is to start from the beginning of concrete. Many of you have been on the field, many of you are constructors, many of you are ready mix providers. What the contractor worries about at the site is placing, workability, fluidity, workability retention, and no plastic shrinkage cracking. That is most of the worries of a contractor at the site. Next comes the mechanical performance, which the designer is worried about. What I want to emphasize is different type of groups of people are worried about different aspects of concrete. The designer is worried about cracking, shrinkage, creep, stiffness, and strength. Then comes the owner who is going to live there or who is going to use that building. They want the structure to last for a long time. They could be attacked, but it has to last for a long time. The scientist, the researcher, has to connect all of these, link all of these, and understand why this is happening. What is the microstructure that is giving that durability or giving that strength? Then comes the service life. As society, we want a structure to last for a long time. A bridge should last for 100 years and not 20 years because we don't have so much resources that we cannot keep doing these things. And finally, and very importantly is sustainability. This is necessary for the whole planet, for all of us. Whatever happens in a different part of the country affects us because the greenhouse gases are everywhere. So this is what I will try to look at and see how we can put all of these together. So before I start, I wanted to present this limestone calcined clay cement, or LC3. We have been working on it for almost 10 years. The idea is to take unusable limestone, secondary limestone, and waste clay, kaolitic clay, and reduce the clinker to 50%. And this is what we call LC3. So we have 2:1 ratio of calcined clay and limestone and 50% of clinker. And what you will see in the later part of my presentation is whenever we reduce clinker in the cement, in the concrete, the carbon emissions, the embodied energy decreases. It is obvious, but I will show you some numbers. So this is one of the cements that we are working on and I will present today. So I will talk about different concretes with ordinary Portland cement common Portland cement, concrete with the ordinary Portland cement and 30% fly ash, and the LC3. I will show results of 3 groups of concrete: a 30 megapascal design strength concrete that I call M30, a mix which has 50 megapascal called M50, and a common mix which has the same binder, same water binder ratio, but different types of binders. All of them have a slump workability of around 100 millimeters. So all of them can be compared with the requirements at the site. We have a good workability, we have the required strength. Now let us see what happens to the other properties so that we can bring it into the framework of sustainability. First, very importantly, dedicated to Paulo Helene is durability. Strength is covered. We know how to get strength. We know how to get workability. But we also have to worry about durability. This is durability based on surface resistivity. As you all know, you must know, because Paulo is here, that corrosion is an electrochemical process. The resistivity is very important. And what we see is the resistivity of concrete has a very wide range. Please see that, note that this is in logarithmic scale. So it is going from 10 to 1000. The resistivity in kilo ohms centimeter. This is the age. And what I would like to highlight is ordinary Portland cement is least in resistivity. And the highest resistivity is LC3 with PFA. Higher resistivity means the ions cannot go, the electrons cannot go, and therefore you have slower corrosion. So we want we want the cover of concrete to have high resistivity. And this we can get by reducing the clinker content, the OPC. What is also important is the age. We see that fly ash is very sensitive to the aging, but LC3 is not. This is also important. If we can reduce the curing time and get the properties, then we are better in terms of sustainability. Now, we already have a hint that we are going to have better durability with blended cements. Now, we look at diffusion. This is the chloride concentration with respect to depth on concrete. Imagine that this is the cover of concrete and we are measuring the chloride concentration from the surface inside. And we can see that in ordinary Portland cement, the concentration inside is quite high. Right? It is more than, it's about 0.5, 0.6 at 10 millimeters. With fly ash, it is less. With LC3, it's even less. Okay? So this means that less chlorides can go into the concrete if you reduce the amount of clinker and have blended binders. And these are the numbers which come out. From the profile, we can calculate the diffusion coefficient. And here I have the numbers for different concretes. We find that, we find that for M30 concrete, the 30 megapascal concrete and M50 and so on, everywhere the diffusion is much higher in ordinary Portland cement. Remember, these are concrete with the same strength, same workability. So we are comparing equal types of concrete. Very big drop. So this means again that chlorides are having trouble going inside when we are talking about these blended concretes. Why does this happen? We looked at the concept of tortuosity. This is based on some work that Carmen Andrade did, and we used that as a reference. So we look at the electrical tortuosity, the path that the charges have to take, the path that the chlorides have to take. And we find that as the tortuosity increases, the diffusion decreases. And it falls into a very nice band. Ordinary Portland cement is here, fly ash is here, and LC3 is here. Remember, LC3 has only 50% clinker, fly ash is having about 65% clinker, and this has about 95% clinker. So again, less clinker, less possibility of chlorides to go in. And we can understand it from the microstructure. Now, when the chlorides go in, they have to reach a certain threshold, valor umbral, that the concentration only when it is higher than this value, corrosion starts. So we wanted to see what happens to that value. So we do this test with a specimen, a bar of mortar with a steel bar inside, put in solution of 35% sodium chloride, and we start monitoring to see when the conductivity increases very highly. So when there is very high conductivity, that means all the ions are going through. The ions are able to travel faster. And at that time, when we see that the conductivity suddenly increases, then we break it open to see what is the concentration of chlorides on the surface. And here we have a different trend. OPC has a higher chloride threshold than fly ash than LC3. So this means that the usual value that we take of 0.4% as the chloride threshold will not work for fly ash and LC3. We have to calculate this when we are doing the service life estimation. This also tells us that diffusion alone is not important. We have to look at different aspects. Now we can put all of this together to calculate the service life. So we took two elements. We took a bridge pier and a bridge girder, and we got the cover that is used, the chloride threshold from these experiments, the diffusion that I showed you. So these are the parameters which have to go in. We have to consider where the structure is, and based on that we look at the surface chlorides, and we also get a decay constant because aging also affects the diffusivity. So with this, we can now try to calculate. We put all the parameters together and we can try to calculate what happens to the corrosion. So I'm presenting this as probability of initiation of corrosion versus age. Higher probability means more risk. So if the curve is higher, that means there is more risk. And you find always that the OPC, the concrete with Portland cement only, is always higher. So that means there is always a higher probability of corrosion than the concretes with blended binders. And just for the sake of numbers, if we say that we take 100 years as the desired life, we here see the probability of corrosion starting. So clearly we see that the ordinary Portland cement is at a disadvantage in terms of durability and service life. We also did the same thing with carbonation. So we have specimens that are being exposed to natural carbonation for more than 10 years, and we are breaking and seeing what is the carbonation depth in these specimens. They are in sheltered and open conditions. Sheltered is more problematic, and I will show you some results. Here what we find is the reverse happens. In carbonation, the concrete which has more OPC is better, opposite to diffusion. Okay? So clearly there is no one single concrete that is good for everything. There is no magic concrete. We have to understand the concrete, its microstructure, and the environment. That is where durability and understanding of durability comes in. And you find very clearly that when you have less clinker, less OPC, the rate of carbonation is higher. So this is also important. So we have to take this into account. If you have an environment which has possibility of corrosion due to carbonation, then this has to be taken into account. So I'll bring all of these back together at the end. So we have seen clearly that even then, even though the strength is the same, durability can be very, very different, and we have to understand this. Now let's go on to sustainability assessment. I'm looking at two parameters here: carbon dioxide emission or greenhouse gas emission, and embodied energy. Energy is also very important because it drives the cost and raw materials and transportation. So if we can reduce the embodied energy, it is also contributing to sustainability. So what we do is use a technique called life cycle assessment. Vanderlei John is an expert on this, and we look at first the system. What are we going to use in the calculation? So I'm going to give results of what is called the ground to gate or cradle to gate. That means from the mine, all the impacts have to be calculated for the product to be assessed correctly. So we do this data collection from plants because in India we do not have a catalog. I think probably in Brazil also there is an effort to collect data, but we don't have data. Yesterday we heard Kasuga-san say that there is going to be an international portal. So we all have to contribute. So what we started doing is sending our students to the plants, to the factories, to collect the data that is going to be used in the calculation. Then we try to look at sustainability from the point of view of the contractor, workability, the designer, strength, then carbon emission and embodied energy and durability, and see if we can put all of this together to look at sustainability. So these are the different plants that we looked at. This is the map of India, and these are different plants. I will show you data from one of the plants. If there is interest, you can contact me and I can give you the data for all these plants. And we can see how they compare with, say, Brazil or other data. So this is the data of this particular plant. It's a reasonably modern plant. It has a 6-stage preheater with precalciner. Present capacity is about 5 million tons per year. And it has ordinary Portland cement, slag cement, and slag as products. Roughly, they are using about 100 kilograms of fuel per ton of clinker, and they also use grid electricity. So first, we have to know what is all the material that is going into the clinker. We have to find out everything that is going into the clinker plus the electricity. So we see that in addition to the main component, limestone, there are other things which are waste materials, like red mud, which is coming from the aluminum industry. It is a waste from the aluminum industry. Flue dust, which is the dust coming out of the chimneys, and some slag. And the fuels are also very much mixed. We use a lot of pet coke, which is coming from the oil refining, in addition to coal, and we use a lot of waste materials. Pharmaceutical waste, solid and liquid, from the pharmaceutical industry. Carbon black from recycling of tires. So this is the residue that remains after the tires are destroyed.